So let's take a look at problem number 5. So hopefully the first thing you're thinking is to, of course, draw the electric field lines between the oppositely charged parallel plates. So if you haven't already, that's sort of how I've been training you to do. Just pause the video, go ahead and do it. And of course, this is our case of the uniform electric field. So all the lines are parallel to each other. They're all evenly spaced, and they're pointing from positive to negative, of course, right? So it just looks something like this. And really pay attention to the details. Make sure they actually start on the positive plate and they end on the negative plate. They don't continue to the interior of either. We'll talk more about that soon. So at this point, just definitely pause the video and go ahead and try to solve the problem. Now, in case you're getting a little bit stuck, well, we're looking for the change in potential. Now, we have a couple different equations involving potential. We have to think to ourselves, should we be using ones for point charges or for uniform fields or for all-purpose equations? Well, we really only have equations for point charge, V equals kq over r. And are we looking at point charges here? Well, we certainly have an electron. An electron is moving from the positive plate to the negative plate. It's a point charge, but is it the one creating the potential? No. The potential's there because of the plates. The plates are sort of representing the mountain, right? The elevation, the possibility of having potential energy, and they create the potential whether or not the electron is there or any charge is there in between them. And so they're not point charges, so we can't use V equals kq over r. Luckily, the original equation for potential difference is an all-purpose equation. So we can probably start with this, that delta V equals delta PE over Q. But we still have to find that change in electric potential energy, so now we have to pick which equation will go along with this situation. Once again, we find ourselves thinking, is this involving point charges or is this involving uniform fields? Well, it's the oppositely charged parallel plates. This is the ideal time to use the equation for potential energy for a uniform field, and that change in electric potential energy, of course, is QE delta D. And so some students might want to combine the equations, other students may want to just solve for the delta PE on their own. Whatever, we're going to get similar answers regardless. Or are we? Well, let's see. If you found the change of potential energy, you're going to find 2.50 times 10 negative 17 joules, which makes sense, right? Because the electron is negative and you're moving it closer to the negative plate, right? If you wanted to define a distance equal to 0, distance equal to 0 would be at the positive plate because it wants to be there. So it's clearly going to where it doesn't want to go, so it's gaining electric potential energy, right? Anytime a system gains potential energy, it's when they're in a position they don't want to be. And the electron certainly doesn't want to be against the negative plate. So students who calculate the change of potential energy and divide by the charge, since the charge has no absolute value sign on it, will get one answer. And students who instead combine equations and realize, oh, we can just sort of cancel out the Q and get this sort of shortcut E delta D, are actually going to get a different answer. So some of you may be getting negative 156 volts, and other students may be getting 156 volts. And clearly, it can't be both. So why don't you pause the video and think which one is the correct answer? And it's not necessarily the one you found, just so you know. Or maybe it is. So here we have to really go back to our definition of potential, because remember, the potential is there whether or not the electron is there. Just like when we talked about our analogy with a hiking trip, the mountain doesn't disappear just because we decide not to pull the cooler of food up to the top or release the helium balloon next to it, right? It's just they are creating the potential difference, creating the elevation. So these plates are creating the potential difference regardless. Now you just need to think about where the electron's moving. So why don't you pause the video and identify positions of high potential or low potential in the system. So now we go back to the idea that positive charges create regions of high potential and negative charges create regions of low potential. So in our analogy, the positive plate is like the top of the mountain and the negative plate is like the bottom of the mountain, regardless of whatever charge is moving around in between. And so the positive plate is high potential, the negative plate is low potential. And now we just actually read the problem and see the electron is moved from positive plate to negative plate, from high potential to low potential. So is it gaining or losing potential? It's losing, right? And so it's actually going down the mountain. And so the correct answer is negative 156 volts. Now that is not going to come from necessarily the math, depending on how you did the math. Here you just have to label the plates and really get a sense of what's actually happening. Okay, let's go on to problem 6 here. Go ahead and give it a read through, pause the video, see how much you can get done with part A, and then come back to see how I solve it. So again, one of the key phrases is how much work did you do, right? So we know we have to distinguish between the work done by the field and the work done by some external agent. If the problem wanted you to find the work done by the field, it definitely would have said so, and here it's not doing that, so this is the work that you are doing. So you may be tempted to say, oh, I know, I'm going to use W equals F delta X cosine theta. Well, let's think about this. The force involved is the Coulomb's law force, right? Because we're moving one point object near another point object, right? And so we can use KQ on Q, K big Q little q over R squared. And just need to think, as the charges get closer and closer to each other, what's happening to that force? Yeah, that's increasing. And so we should know, of course, to use this equation, we can only use it if the force is constant. And we can't do that here because the force is clearly not constant. The other issue, hopefully you realize, is what would delta x be? If one charged object starts infinitely far away, that means that delta x is infinity. Well, good luck doing that, right? That's just not going to work. So clearly, this is not the equation to use. So the question is, what equation can we use? Well, we are assembling a system of point charges. And it takes work to do so, which means since these charges don't want to be near each other, we're really storing electric potential energy in the system. So we should be using this equation, W equals delta PEE. Now remember, this is not an official new equation, and be very, very careful you're not mixing this up with the work done by the field. W sub E is the negative change in electric potential energy, but this is not the work done by the field, this is the work done by us. And if you recall, they're almost always going to be opposite to each other unless you're given more information. So from this perspective, now we know it's going to be a change in electric potential energy. Well, what potential energy equation should we be using? Is this a uniform field, or is this point charges? Well, this is clearly not a uniform field. It has nothing to do with oppositely charged parallel plates, so this is the time to use the point charge equation. So it's the change, of course, is final minus initial, is the change in the quantity K big Q little q over R. Now we see the information that one charge starts infinitely far away, and you'll recall we define infinitely far away as the position of zero electric potential energy, so that term is going to drop out, and now it's just a matter of putting the right numbers in and solving. As always, pay careful attention to the units. You notice the distance is 2.5 centimeters. I'm sure you all caught that. But also take a look at the charges, right? They're in micro coulombs. You need to remind yourself what the prefix micro refers to. Of course, that's 10 to the negative 6th coulombs. And so we should be getting 3.29 joules. All right, go on to letter B. Pause the video, solve it, and come back to see how I do it. So what's going to be our approach here? Well, certainly when you let one go, the other one's going to be forcing it away. Can we do anything with kinematics and dynamics? Sigma F equals ma. Well, once again, we have this idea that as they get farther and farther away, the force between them changes. Specifically, it gets smaller and smaller, which means the acceleration is going to get smaller and smaller. A changing acceleration, you can't do kinematics. But what's always our go-to when kinematics fails? Sure, an energy approach. And we know that this is a conservative field, so we can do some conservation of energy. So if you didn't quite get that, maybe you want to pause the video and try that. But as always, I'm going to write out the law of conservation of energy in full, where this is, of course, involving an electric potential energy. And now we do our usual game of what's going to be zero. Well, it says this starts from rest. We know the initial kinetic energy is going to be zero, and it's going to an infinitely far away position, which remember we define as the zero position for potential energy. So we can cross off the initial kinetic energy and the final potential energy. We just found the starting potential energy, right? We assembled the charges and we stored 3.29 joules of energy. So we don't need to recalculate that. So we can replace kinetic energy with 1 FmV squared and then just rearrange to solve for the speed. However, we want to be very careful. Which mass do we put in here? M1 or M2? Because we're given both masses. Well, hopefully you see, of course, that it's Q1 that's moving, so it's Q1 that has the kinetic energy, so it's M1 that gets the energy, right? So we're putting in mass 1 in there, so go ahead and calculate. We should be getting 1.28 times 10 to the 5th meters per second. And what do you notice about that speed? Yeah, it's really large, and that's very typical in these sort of problems. We're kind of used to finding very, very large speeds involving these tiny, tiny objects.